Next, we want to sketch an example of a line with a positive slope. It has a positive slope. It's going to be increasing from left to right. So this right here is something that has a positive slope, versus negative slope would be decreasing from left to right. So this line right here would have a negative slope. Now, a line that's going to have zero slope needs to be horizontal, and a line that has undefined slope is going to be vertical. So these are straight up and down or straight left and right for zero slope and undefined slope. Positive slope could be a variety of slants, whether it's sloping very steeply up or shallowly up, but it's heading upward versus there's that trend, upward trend, versus a very steep downward trend or a less steep downward trend. Okay. In objective 2, we're going to use slope to talk about parallel lines. Okay. Two lines that do not and will never intersect are called parallel. This is the definition for parallel. And to think about what these look like real quick, a parallel line, these are my x and y axes right here. Two lines that are parallel are never going to intersect. So they're going to look something like this, where they're never going to intersect. They're heading off in the same direction. Same direction means they're going to have the same slope. Okay? So in example 6, we're going to determine if the line passing through 2, 0, and 0, 6 is parallel to the line passing through 1, 8, and 0, 5. So the first line's slope would be y2 is 6 minus y1 is 0 over x2 is 0 minus x1 is negative 2. So that slope is going to be 6 divided by 2, or 3. And the slope of the second line is going to be y2 is 5 minus y1 is 8 divided by x2 is 0 minus x1 is 1. So I've got negative 3 divided by negative 1, which is 3. Okay, so the slopes I got were the same, and since they're the same slope, it means that the two lines are parallel. In the next objective, we're going to use slope to talk about perpendicular lines. Two lines that intersect at a right angle are said to be perpendicular. This is the definition of perpendicular. Oops. And the slope of these two lines, okay, let's talk about that for a second. So my example, if I draw my x and y axes, I'm going to use my line tool here. So if I draw one of my lines like this, to have a 90-degree angle, my other line needs to look about like this. That looks like it's a 90-degree or right angle. And so what we can see about these two lines is that, first of all, I notice that one of them has a positive slope and the other one has a negative slope. I can also see that one of them is increasing slowly. It's a rather slow approach, whereas the other one is quite rapid. So they're opposites in that way as well. So the slope of these two lines are called opposite reciprocals. The opposite part of this refers to the fact that they are opposite signs, one's positive and one's negative. And the reciprocal part of it refers to the fact that one is very steep, where the other is very shallow. So we have very steep and very shallow, so the slopes are reciprocals. Opposite reciprocals. So, for example, two numbers that are opposite reciprocals might be like 3/2 and negative 2/3. One of them is positive, the other one's negative, and the fractions 3/2 and 2/3 are reciprocals. Or another set of reciprocals might be negative 4 and positive 1/4. Those would be reciprocals. 4 is 4 over 1, so the reciprocal is 1/4. One's positive and one's negative. Okay? So in example 7, we're going to look at the two lines given by these ordered pairs right here. The first line goes through 1, 5, and 0, 3. So its slope is 3 minus 5 over 0 minus 1. So I've got negative 2 over negative 1, or 2. And the other two ordered pairs, the slope right there is going to be 6 minus 8, y2 minus y1. And x2 minus x1 will be 2 minus negative 2. So we have -2 divided by 4, or -1/2. These are opposite reciprocals. 2 is 2 over 1, so when you flip it you get 1/2. One's positive, one's negative. So the two lines are perpendicular. Alright. In example 8, we're looking at the fourth objective, talking about rate of change in applied situations. So if the temperature is increasing from 60 degrees Fahrenheit at 7 a.m. to 68 degrees Fahrenheit at 8 or 11 a.m., estimate how much the temperature increased per hour. Okay, one of the things we can do is to organize this information in ordered pairs. Okay, at 7 a.m., the temperature was 60 degrees. At 11 a.m., the temperature was 68 degrees. Okay. Now, why did I put the 7 a.m. first and the 60 degrees second? That is an important question, and there's two ways of thinking about this. The x variable is always the independent variable, and the y variable is always the dependent variable. The time is going to be independent, and the temperature will depend on the time of day. So my independent variable must be the time, the hour, and the dependent variable must be the measurement in degrees. Another way of seeing this is to look at the units in the answer we want. I want a measurement of temperature increased per hour. I know that per is a division word. Okay, so this is temperature divided by hour, and I know in slope I'm going to have change in y divided by change in x. Okay, change in y divided by change in x. So that is telling me that what I have first right here must be the y, what I have second must be the x. This is my division. Okay, so that's another way of getting your ordered pairs organized. Your answer is not going to be correct if you have them in the wrong order. Okay, so there's a couple different indicators there. If I want to think about the independent and dependent variables, or if I want to look at those units and know that I know it's y divided by x for the slope. So it's telling me that y is temperature and hour is x. So when I put them in the ordered pair, it's x comma y. So it's the 760 and the 1168. Let's go ahead and find that slope now. So that slope is y2, which is 68, minus y1, which is 60, over 11 minus 7. Okay, 68 minus 60 is 8. 11 minus 7 is 4. So my answer is 2. Now, because this is an applied problem, I need to make sure I put my units back on here. My units I've already circled in red. They're going to be temperature increased by hour. So the units on temperature were degrees Fahrenheit. So it's 2 degrees Fahrenheit. Per, I can either write the word per or I can use the slash for per hour. So this would be my final answer. So I'm computing a slope here between these two sets of data, and then because it's a rate of change, because it's an application problem, just making sure that I put appropriate units back on the end of it. Okay, let's try that again in a different context. In example 9, construction laws are very specific when it comes to the access ramps for disabled. The grade of the ramp refers to its slope as a percent. Every vertical rise of 1 foot requires a horizontal run of 12 feet. Okay, what's the grade of the ramp? Okay. Now, they don't give me two different ordered pairs in this case. I can draw a picture if it's going to help. Let's see. I've got a ramp, and they say that for every vertical rise of 1 foot, there's a horizontal run of 12 feet. Or I can think about that slope again and know that it's the change in y over the change in x. And they've already told me what the change in y is. They didn't need to give me two ordered pairs to know how much it changed. It said it rises 1 foot for a run of 12 feet for a change in 12 in the horizontal distance. Okay. So let's go for a decimal right here, because I'm going to need to make this as a percent. So 1/12 is 0.0833. Repeating. Alright, and this is my decimal. I want to make this into percentages, so I'm just going to move the decimal place twice. So my answer is 8.33%, or they asked me to round to the nearest tenth of a percent, so I really only need to write down one of those threes. Okay. And we've reached the end of the section.